Welcome, everyone. It's great to see such a full house at today's Center for Data and Computing lecture series. Today, we are very privileged and pleased to welcome Alex Gray, who is the Vice President of Foundations of AI at IBM. He leads all of IBM's basic AI research around the world. Prior to IBM, he also founded a company called Skytree, which is basically developing systems for large-scale machine learning. And prior to that is actually where I met Alex, where we were on the faculty together at Georgia Tech for, I think, almost 10 years. A lot of his work basically has been involving processing of really large data sets across a wide range of domains in science and networking, network security, as well as it's something that Alex and I worked together on. And actually, Alex converted me to the Church of Machine Learning probably 10 or 15 years ago. And if you read his bio, it talks about how much of his work has been in applications of machine learning for massive data sets, predating the meme big data. And I can certainly attest to that. Alex and I, as we worked together on the faculty at Georgia Tech for many years, both in research and in education in the PhD program there, we'd often spend many weekends together sitting in coffee shops doing our work. And I remember every time Alex would meet someone, he would ask them, do you have any problem that involves a lot of data? No matter who it was, he would basically ask that question. And at the time I actually thought it was strange, but it's just a testament to, that was like probably 2006, 2007. It's really a testament to Alex's vision in this area. He is definitely a pioneer in the area of big data. And I think another thing that I think is really fantastic about Alex is his singular focus, not just on the math and on the foundations, but in also making this real. That's actually how we think to work together, is he wants to see the algorithms and the basics and the foundations really put into working systems to change the world in areas from computer systems to science. So let me ask you to join me in welcoming Alex for today's distinguished lecture.
All right. Hey, thanks everyone for having me. And I really just came here to visit Nick, and then discovered all of this, which is very impressive. Hugely impressed with what's going on.
Sorry, could you use the mic, please?
Oh. How about that?
Yep.
Better? Okay. All right. I was just saying, Nick and I go back a long ways, and thank you, Nick, for the kind introduction. I really was here just to visit Nick, and then found out about all of this, and very, very impressive. So looking forward to hearing even more about what's happening here. It's a great time for this topic, of course. It's an old topic, but I'm sure you know there are many new wrinkles that really haven't been developed enough. So. Just how I got here, or the thing I'll show you really is just one idea, one simple idea in a way. But I arrived at it just after encountering many data science problems I started as a data scientist, what would now be called a data scientist. Back then it was not called that. At NASA, and really did a whole bunch between that and working in company land, and working with scientists mostly, and then working with enterprises mostly, and all sorts of other things in between. Maybe 150-ish kind of problems, and you know, some of them not, you know, for weeks, just like a taste, but still, you pick up some things. You see a lot of common patterns. I mean, and this little idea occurred to me as one fix for some of those problems. So this is actually a very partial list of people represented in this work. So here's what I'm going to talk about. First of all, we need to define data science to do what I'm going to try to do. I'll just give you a few qualitative kind of points about, I think, sort of what's wrong with data science today. And then motivate automation of data science and how should it work eventually. And then how could we actually formalize it? So, you know, when you try to do something like that, you're destined not to succeed fully, but I'll hopefully at least capture something useful. That thing will be called meta models, and it'll turn out that a big question is how you oppose a kind of ambitious thing. It'll be tough to compute, and I'll show you an attempt to compute it, and then show you how this might be expressed in some practical tools. Okay, so roughly speaking, this is data science. This is what I call data science. It's a whole bunch of steps that I'm sure you've seen a million times in different talks and scenarios. Data ingestion, data feed. The meaning of these things is a little ambiguous, but I mean a certain thing by them. Data cleaning, creating new features, maybe certain transformations on all the features. And then finally, the one part that you actually learn about in school, which is the modeling part. That's where you can actually get a textbook, and it's all formal, and there's a great grounded theory. Okay, that's the theory of machine learning or statistics. I would call it all multivariate statistics personally, but a lot of what is called machine learning. Then there's this last bit, which is deployment, which is actually, even if working in academia, you're going to have to prepare data to do some applied ML problem. But deployment is something you really encounter in a big organization. So what I mean by that is, okay, you've made a great model, at least it looks great, based on your training data. And then it's going to go on some server somewhere, serving predictions for something, like scoring people's loan applications or diagnosing people for cancer or whatever it is. Okay? And then eventually, there's another issue with that model. It becomes stale, and then you got to retrain it. So you got to go around the loop again. Okay, that part I'm not going to talk about today. It's a very important part that's also not addressed very well in textbooks.
I'm sorry, but I know the microphone is on, but I don't know if it's not on.
Oh.
Enough, or if you could try to speak
Up more.
bit louder.
Okay, I'll just try to be louder. Unless there's a way to bump me up.
There's a volume. We're working on it.
Okay, okay. Okay, sorry about that. I'll try to be louder. So I'm not going to talk about deployment today. Maybe the next time I come, if I do get invited to come next time. I'll talk about that, because that's something I'm also working on with my team. So, but data prep. We're really mostly going to try to treat this data prep stuff. So this is what I meant in my little abstract, that why data science, it's these two parts, data prep and deployment, that are not formalized. And most people, if you ask them, even working data scientists would say, yeah, that's because you can't formalize it. It's really complicated. There's so many things that you do to data. It's all dependent on the problem. It's domain specific. You just have to hire somebody who's an expert in, or has experience in finance data or whatever, medical data or something like that. Okay, so it gets the term munging. Munging is exactly captures how people think of it. Whatever, it's a big ugly ball of blah. Okay. The textbook, when you get all the way to the modeling step, the textbook, for machine learning or statistics, multivariate statistics, starts with let A, your data, be a matrix. Then we proceed. Okay? But how do you get that matrix? It turns out that's 80% of the time. It's widely quoted, and it's true. It really is pretty accurate. Okay? Why is that? If it's a completely unintellectual part of it, it's so important. Apparently, it takes up most of the time. It turns out, in fact, here's a big, we think, yeah, that's just some stuff you have to do, but the real magic is in the modeling. Actually not true either. The choices of different models and so on give you minuscule differences, typically. It's actually the choices in data prep that give you the most difference in the final accuracy. Okay, you have good features or bad features. You have clean data or unclean data. It makes a much bigger difference in the final result. Okay, furthermore, data prep has parameters too, typically, or often. Okay, sometimes not, but many times yes. Would you guess that the choice of those parameters might affect the final accuracy down the line? There are things like bin column 7. How many bins? 7 bins? 3 bins? PCA is an obvious example. Well, do I keep the first 3 eigenvectors or the first 14? Okay, so those things are never tuned, by the way. Hardly ever. Like people just think of it, this is a pre-step. All this data prep stuff is a pre-step. Whatever, make some choices. It's just, before we get to the action. Okay, now, I'll point out some conceptual errors that actually are not taught the right way to think about it is not really taught very explicitly either. I'll point out a few. It turns out if you read closely enough in, say, the Hasty et al. Book, which is a great book, it does have a little section on some of the things I'm talking about, but it almost never, my PhD students would never remember that part, or few people read that part. So it's not really emphasized. The kinds of errors that can happen by not thinking clearly about data prep or deployment. Okay. The other thing you realize in data science, you're trying to do something generally kind of important, hopefully. It's important to somebody. And they're different. If it's a big enough thing, there are multiple stakeholders. And they all provide some kind of constraints on the solution. But it's generally not handled in any principled way, the desires of all these stakeholders. Okay, so here's examples of stakeholders. Let's say this is loan application, or you're predicting loan default or not. Okay, this is pretty important for you if you want a loan. So this probably is done by an algorithm today. Your insurance rates and all that. We're not even talking about medical applications where there are much more serious consequences, and therefore more stakeholders and so on. But even something like that, there's a regulator. This is like a person from the government who imposes some constraints. Well, you can't discriminate against certain groups and so on. This is in law. Okay, so these are real constraints, explicit constraints. Even then, even though you would think the law is crisp, it's a little mushy, and how this gets incorporated into the final solution is like conversations, if you can believe that. And different parts of that process I showed you are done by different people, different teams sometimes. So they're really passed off in phases. Okay, that's a typical thing. Deployment is done by a deployment team. Data prep sometimes, especially early data prep. That's the database people. They're going to do that. In some companies, they even have a firewall between these groups because they don't want certain people to have the full access that data scientists have, say, to all the variables. Okay, so it ends up being this kind of, let's just say, not well-defined mishmash of decisions that all change the model in different ways, sometimes through the data prep. Okay, all right, and yet they're all important. The final solution has to somehow have incorporated all these different desires. So some desires are, for example, well, I need the model to be as accurate as possible. Okay, that's the classic statistical constraint, you could say, the data scientist, what the data scientist thinks about. But over on the deployment side, hey, this model can't go into production because I need the prediction time to be less than 30 milliseconds. You can't, let's say it's credit card transaction fraud detection. You need an answer right away. You can't use a model that's, going to take too long. Okay, so that's a constraint that eventually does affect the choice of algorithms and so on. All right. Another example is the regulatory constraint that I gave. Okay, so now what I noticed a lot, even PhDs, big companies, the leading company in some space, like a multi-billion-dollar company, PhDs from wherever, Stanford, wherever. That's a big on them, but smart people. But it's because of all these different interactions and so on, and also I think just not paying close attention in the textbooks themselves, that you get at least these three kinds of mistakes. So it's very common that the data scientist makes some kind of pipeline. Pipeline is the sequence of data prep steps, and finally the model. But then that was done a certain way in training, and then at deployment time or test time, it's done slightly differently. It's sometimes even coded up by different people for efficiency to run on a mainframe or whatever it is. Okay, so, or a different tool that they're using for deployment. Okay, so right away you have a breakage of the sort of ML, canon, which is whatever you do in training, you have to assume the train and test distributions are data sets are from the same distribution. So, okay, so if you're not even doing the same thing at test time that you thought you were doing at training time, it's sort of chaos in the worst case. So another very common thing, this is the one I was referring to in the Hasty et al. Book, is because when you think of data prep as people do, as a separate phase from modeling, then you do things like, I would give this verbal quiz to PhD students in machine learning and statistics. Yeah.
So you mentioned textbooks. Do you expect that most people who are implementing these or even creating these methodologies are learning from textbooks in class or learning on the job? I feel like a lot of CS professionals nowadays might not have a technical CS background from like a university, so they may never read a textbook about this kind of stuff, and they learn on the job.
That's a good point. That's a good point. I hope, well, we'll come back to the state of data science education, even formal education. But it makes it even worse, right? People don't even use formal education. Then I think our hope here is, if some of these kinds of things are right, then code them in the tools. So the tool will not let you make a mistake.
As a follow-up, as working in industry in IBM, do you make it a point to try to educate those that are possibly building these technologies, or do you expect that they already have this perfect knowledge?
So we have whatever thousands of data scientists, for example, and I'm on the data science board of education board. So yes, I try to do that. We have another council for like AI education internally. IBM has 400,000 employees, so it's like its own nation. So it's very hard to reach everybody and so on. So, so yes, we try to do that, but I think it's more to your first point. Many people will never, they're practicing data science, they're not going to go back, and if I make a course, they're not going to go back and learn it. So I think my ultimate answer is you got to build it into the tools. The tool should not let you make a mistake.
And along with that, this changes every year. The security vulnerabilities and the advances, and especially data science, changes every year. So someone that may have this background may not be aware of like the up and coming issues or the possibilities they can have. So my question was just like, if you guys are actively involved in current education and among people that are doing this.
We try, but like you said, you know, it's education is a snapshot now and into the future, but it doesn't address working data scientists.
I think we're just going to hold the rest of the questions for right now so we can get through the talk, but thank you.
Good question, though. So second one that's common, I would ask a PhD students in a class, is the following okay? You know, bin column 7 and then do this and then do this. Then do a PCA. Okay, now you've got your data set. Now do your modeling stuff, which is, you've got to do k-fold cross-validation. Is that okay? Sort of seems like maybe it is. No, it's not okay. The PCA has seen things that are going to be in the test data that happens in k-fold cross-validation. You've got what's called data leakage. Okay, so you're going to overfit, okay, because you've cheated. K-fold cross-validation is supposed to be the thing that prevents you from overfitting because you hold out data. But in your data prep, you're not doing it if it's holding out of data. And if the PCA makes it hopefully kind of obvious, that thing is very much like a model. Okay? But then if you keep thinking about it, there's other stuff before, even simple stuff. Take the log of column 8. That's also kind of a model. Okay? Some of them have parameters, some of them don't. Even a log is not that consequential, but the base of the log, everything has some kind of parameters. Almost many things. Okay, so that's one kind of error. And that can be pretty bad, actually. And then as you'll see, well, as you know, modern methods are non-parametric. And we're talking often about differences of 0.5% or 1%. In an enterprise setting, an important problem, that can be $50 million difference in value. Okay, so overfitting a little bit maybe doesn't seem like a problem. It's kind of a problem. And then I've seen much bigger differences now, like 10%. Okay, so, and then the last thing is, well, I've kind of mentioned already, mitigating overfitting.
Sorry, I have a real quick question.
Yeah.
You're basically saying that if I 0-1 normalize, for example, my data before I feed it through my model in training, that I've overfit. But the thing is that we use that 0-1 normalization in test.
It depends. I mean, it depends. If it's something that we're having seen test data that you shouldn't have seen affects what you do, the rest of the data, then yes.
So in the
But in some
particular
things it doesn't.
you're talking about in the particular instance of k-fold cross-validation, if I use this to choose k, but if I carry it through all the way and into test, it's not such a big deal? Like the 0-1 normalization parameters, for example. If I use them in test, this is not data leakage?
Normalization can actually, yes, if you have you know, differences in your folds, that you have some large values and so on. Yeah, I can make this. I'll show you the final, how do we resolve that? So it won't all be just problems. How we can resolve it. Okay, so here are my little pictures. So we have no equivalent of regularization, for example, in data prep, right? PCA is the closest, you know, that kind of a thing. Then you're like, oh, okay, that's kind of like a model. Maybe I'll regularize that. But otherwise, no. Okay, so here's my summary of, these are not all the open issues in practical data science, but the ones that I'll try to address. Okay, black art, manual, siloed. So, of course, now, why? Why should we automate? Well, it depends. It may seem obvious. There's some obvious benefits. It kind of depends who the audience is. I'll get more into this. We do actual surveys of people. Well, if you're not an expert, maybe you can get up to the expert or near expert level. Then you should be happy. If you're an expert, sometimes you're not happy because you think you can do better. Maybe you can, maybe you can't. But we see that. They're not necessarily happy. But eventually they get used to it, typically. And then once they understand how they can control it, which we'll see, then it can save them time. They understand it can take away some of the mechanical aspects of data science. Okay, but I'll come back to that. And then, you know, the person who owns that problem of like good scoring of loans or proper diagnosis of cancer worries about the reliability and consistency of this application. Okay, which, if you think about it, it's all highly manual today. It's all done by gurus. There's typically one or two. This is the guru in the company who is the data scientist who really understands what's going on and did all the right data transforms and so on. Oh, now that person left to go to Google, go to Facebook, whatever. Our models are not as good anymore, and so on. So there's an actual, as far as an ongoing operation, risk with investing everything in the black box of people's brains. Okay, so here's the first simple idea, kind of. Data prep, obviously, as I hope I showed you, affects your model, right? Which, you know, if you've done you end up with a different data matrix A, you might choose a different model, right? So the choice of data prep affects the choice of model downstream. But the choice of model also affects the data prep, because if it's trying to use a support vector machine with a Gaussian kernel, well, I need to do data prep steps to normalize everything. First of all, everything has to be continuous. All the columns need to be continuous and normalized. Okay, so in other words, data prep affects modeling, modeling affects data prep. So they really should be a joint decision. The choice of those in both parts needs to be done jointly. Okay, so the simple idea is don't think of the model as this thing by itself and the data prep as a thing by itself. That whole thing is the model. The pipeline is the model. The model extends all the way to the beginning. Okay, because those things really are model-like. They are, from the standpoint of the raw data, they are functions on the data, and the final estimator at the end is also a function. They're all just functions that transform the raw data. Okay? We call that's what I'm calling a meta model. We'll see why, hopefully. And then the second simple idea is especially once you can think of it that way, let's form one optimization instead of all of these teams working on parts of the problem, doing their own optimization effectively in isolation. It should be one joint optimization. okay, that accounts for all of their constraints explicitly too. Right now, that's another problem. It's not even written down clearly what all these constraints are, typically. Okay, so what do we aspire to build with something like this? We've got to start with a formalism for data science that just says, in particular, captures data prep in some way that you can make computational. Okay, then you can, you have to have a way of writing down all of these constraints, real-world constraints. Then you can form a big optimization problem, and then that thing will search for the optimal, not model, but pipeline, and then that thing will satisfy the constraints. You put that into production. Okay, that's the idea. Let me stop there. Any quick questions so far? Okay. So then, how do we start formalizing? So here's a picture of the idea. For those of you who are familiar with scikit-learn, right, it's this very simple abstraction. You have data prep steps are transforms, and then at the end of the chain, you have a model, or aka an estimator. Okay, so here, rectangles are data transforms, and triangles are estimators. So in this simple example, and dots are data in intermediate. Every one of these things, the data is the input, and then you could say it's a transformation of the data. So it's a dot before and after each box. So you start with the data on the left, and then we're going to say, okay, with one copy of the data, or take the log and do PCA on the features. We're going to concatenate that with just all of the original features, and we're also going to do something else like the predictions made by a random forest, and make that another column and concatenate that. That's a kind of a thing a data scientist might do. So you're going to end up with a bunch of columns. The arrows coming in mean we concatenate them, and then maybe we'll scale them all, and we'll send that to an SVM. Okay, that's a typical kind of pipeline. Now we drew a big triangle around the whole thing, because in our new concept, this whole thing is the model, including the data prep functions. Okay, so we can think of the whole thing as an estimator. Now you see I've written it here in function composition form. For those of you familiar with that, which is sort of backward. Okay, so that's just to emphasize the whole thing is a function. All these things are a function applied to a function applied to a function. Okay, so that should make it clear why those things are part of the model. They're just, in a neural net, it would be like taking the first layer if it's doing normalization or something, effectively, and calling that a separate step. No, it's obvious that's part of the model. Okay? Now, we just need a way to kind of formalize these data prep steps. We just use a simple idea of a grammar, computer science, basic computer science tool. And we just say that there's some grammar that defines the space of all, and every sentence in that grammar is a legal pipeline. Okay, so you have a start symbol in a grammar, and here, remember, it's backward because it's function composition. You have data, and then you have this meta model. The meta model is, this DAG is all the data prep steps, followed by the estimator, but because this is function composition, it's written backward. And then, okay, that's what this means. Okay, and then these are all the different ways you can glue together things to make a data science. In fact, it's not a pipeline. Pipe, as in linear chain, is a DAG. So because real world pipelines are actually DAGs. Okay, and then this is to break this down, this grammar step, grammar rule. You can either, a DAG can pop out and be an estimator, or it can have in it a transform. It can be a composition, multiple steps. And then this one, if you're familiar with Python, this is a Python term, horizontal stack. This just means this kind of composition. Okay. So, and then to add semantics, that's syntax. To add semantics, we have some types on things. And then later you'll see we'll make them real types in the programming language sense. Okay. So, your data has some discrete columns. It has some continuous columns. It has some columns where you can have missing values. And it's discrete, and somewhere it's continuous and discrete. So anyway, you can write this out as a formal function class. This is defining a set of functions, right? Then your estimators, well, you expand that out, and you have the usual estimators like random forests and decision trees and neural nets, GLMs, and so on. Okay, and you can have subtypes of things. This one is interesting. So if you ever, so we looked at all the Kaggle competitions that we could find. Kaggle is this data science competition thing, and to see what do people pragmatically do to win data science competitions. So we mined that to get all kinds of tricks. We try to fold all of those tricks into this grammar. Okay. And that, to me, was evidence that this simple idea can capture basically everything I've ever seen data scientists do. Okay, so I claim, I'm sure there's a case that we don't cover, but I claim it's pretty complete. So this idea that you can't provide any formalization to real-world data science or data prep, I don't think so. It's just a large set of things, but you can capture. And I'll show you another list later. So one of those things that became very widely known is if you do an ensemble, and there are various kinds of ensembles, then you'll always get a boost, right, basically. Okay, so, but an ensemble, people typically use fixed packages, meaning a random forest is a certain kind of ensemble where everything is exactly the same, a decision tree, so on. But you can have heterogeneous ensembles. But there's no real great function. You have to hack that yourself. Okay, and that's what people do. Meaning, it's an ensemble of a nearest neighbor and a neural net and this and that. Okay, so it's a very easy way to express that as a grammar. And other things that people do, like which are sort of tricks, like let's do clustering, and then we'll get for each of the k clusters, we'll learn a different model on those clusters. That's a simple trick that we can also express as a grammar, in the grammar, and so on. Okay, now let's look at transforms. You've got unary transforms, like take the log of one column. Binary transforms, like add column A and column B, or divide column A by column B. You have things that operate on the whole table, like NCA. And then we have this, we probably should have called this projections. Pick out certain columns that have certain properties. Okay, this is just to show you that, I won't go through all these, but kind of anything you can think of, I think. Tell me if there is something you can think of that maybe we can't do. Okay, pick out all the skewed columns, whatever. You can write a very, very extensive grammar if you want. And these we haven't put them all in, but if you stare at this, there's just a lot of tricks that people do, both in research papers and in data science. Just even simple things like, I've got a classifier. It is a two-class classifier, but I want to use it for a multi-class situation. So you do this one versus all trick, which really is a what we call a higher order estimator. It's a thing where you plug in any classifier, and it gives you a way to put them all together. That's what I mean by higher order. It itself, it's an operator that takes in an operator. Okay, and there are many, cross-validation is like that. It's an operator that takes in as its input a model, which is an operator. Okay, so many things are like that, and yet they're not really formalized in any way. They're just a whole bunch of little tricks.
I have a question.
Yeah.
In your grammar, do you have either conditionals or loops or recursion?
There's definitely recursion.
So higher order patterns, right?
Yes.
So how is this grammar, it's essentially, it's Turing complete, right? Like that's basically what I was getting at. If you have recursion, you have a Turing complete language. How is this, so I think where you're going with this is that you're gonna have a specification language for specifying.
You'll see. Bring up your question later after your.
Sure.
One upshot is it's going to make a big computational problem. So that's maybe where what you're hinting at. That's true. But here's, in a way, if it's the one slide where, it's good to have walked in and seen this slide and then you can go home. It's this one. This is the main idea. This is the upshot, which is this is our one optimization problem. And now we've got this idea that our model is no longer just the estimate at the end of the chain. It's the whole pipeline. Okay, so we're optimizing for the best P pipeline. Pipeline is an element of a grammar. The grammar is defined there on the right in this grammar-ish way. Start symbols and terminals and so on. Okay, you got parameters. Some are continuous, theta, upper C. Some are discrete. And then you've got some constraints, which are these stakeholder constraints. Okay, and you've got your usual notion of loss over on the left, or something like predictive accuracy, or area under the curve, or whatever. And then you've got some regularization, just like you have in a machine learning method. Okay, that can be on the length of the pipeline. That would be the natural thing to regularize. That's the complexity of this model. And then don't worry about this H thing, because we didn't actually implement that yet. But that's potentially a way to put in data science heuristics, which are like, maybe I prefer whenever I see a skewed column to do a log. That tends to work. So I'll just encode that in. Okay. All right, so this thing is itself, that's the big idea, kind of, small, big idea. This thing itself is a machine learning method. And therefore, we can treat it with all of the machinery of machine learning or multivariate statistics. Okay, so anyone can make a new machine learning method. You just have to have a loss function, or you just have to have an objective. And then you have an optimizer and you have a model class. Okay, once you have those three things, you have a machine learning method. But the key thing you always do with the machine learning method is you cross-validate it or otherwise control its complexity to ensure generalization. Okay, and we're doing this now in the whole pipeline. Is the little idea here. Okay, now let's just quickly, because all of you took statistics, maybe, just the terminology, the usual terminology, and just look at this a little bit as a model class, a new kind of model class. I don't know what the name should be actually. Meta machine is all that we could think of so far, because these are meta models. F star, you're trying to find the F star, the best F or function in this class. You've got the usual loss function and so on. I like this diagram. Personally, I think about things this way. You've got the usual things, samples and empirical risk and so on. But let me just show you this. Oops. So this, if you haven't seen it before, this is the way you think of it. Think of things in statistics. You've got your model class. You've got the real thing, which you don't have access to, F star. You're trying to get F star. You've got a model class, if you choose the class of all linear models, that's one choice. It may be a good choice, it may not be. That's your cloud. You can only find models, all you can do is find the best point in your cloud. Okay, you have to make a choice of model class. And then once you've done that, there's some F bar, which is the best thing in that class that best fits the data. It still may not be that you reach F star, but it's the best you can do with given your choice of model class. And then you've got some samples. You got 100,000 examples or whatever. And the best you can do is based on somehow estimating something based on those samples. Okay, and then so right away you're going to have some difference between that and F bar. F bar is if you had infinite samples. Okay, if you knew, you could see everything. So right away you can't quite get F bar either because you're limited to your samples. And then F squiggle is the fact that you can't even necessarily reach F hat because you're doing an optimization fit, and that optimizer has some error. You may not reach the best optimum. Okay, so all these are different ways, different sources of error. So with respect to F star, what you end up with is F squiggle, but that has a bunch of errors with respect to all of down this chain. Okay, so these are sometimes called the optimization error, estimation error, approximation error. Okay, so by taking the model, what's usually just the model at the end of the chain and expanding it, we're expanding F. The model class is now bigger. So that's good for error because it means we're more likely to be able to reach F star. We have more expressive power. Okay, and you could think maybe that's sort of a guide. That's like in some cases why we're doing certain data prep steps. We're effectively increasing the functional representation power. So this is sort of hinting at. Then that's the main thing we're doing. But the upshot is, two bad upshots kind of are maybe we make the optimization harder. We might, so then, this source of error essentially boils down to the efficiency of your optimizer. Okay, because you only have a finite amount of time in practice that you're going to run things. And if you can find a good optimum in that time, then that's what you're going to use. So, and then you have to prevent overfitting. And the default would be k-fold cross-validation or something. Okay, but again, that's expensive. And so in a way, it boils down to the efficiency. Also the statistical efficiency or statistical quality of that estimator is in there too. But these issues, okay, by making a problem more complicated, we make these things more complicated. Is one upshot of having this very rich language to describe the model class. Okay, but hopefully you can see now that the pipeline is the object. When you train the pipeline, you move the whole pipeline into deployment, so you never have this deployment error where you're doing a different thing in deployment. The whole thing moves as a unit, data prep and model. You can never do different data prep in deployment. The whole thing is a package. Okay, you'll never get this data leakage problem because you're always doing cross-validation on everything that's inside the package. And overfitting in data prep you won't have for the same reason. Okay, it effectively gets regularized the same way. Okay, so and furthermore, you're exploring many more possibilities than a typical data scientist does when he or she chooses those data prep steps. They're usually just this. They don't have time to do a combinatorial search, typically. I would do that actually, because I would think in this way. I would go, well, let me take some notes here. Try normalizing column 1, normalizing all the columns. And then I got to explore all these possibilities. But then I have to explore if I didn't normalize all the columns. Now I do all of these things. Okay, so it took me a long time to do my data science problems because I thought this way. So boils down to one big issue is, can we optimize it? Well, for what's a decent way at least to try to optimize it, this problem. Here's the formal statement of the problem. Basically, the z's are the discrete choices of, you know, which nodes are in your DAG. And then you got the discrete and continuous parameters, hyperparameters, really. Okay, ADMM, I won't go through it, but if you're familiar with ADMM, it has this ADMM has these 3 steps. This is a black box optimization. That's why we can do arbitrary anything inside. It's a black box optimization. Black box means I can't take the gradients of the thing inside. The pros and cons. When you can take the gradients, you'd be much more efficient. But this lets you basically do anything, including data prep, and including, as we'll see later, arbitrary constraints. With the constraints you just have to be able to evaluate the constraints. Okay, that's important because business type constraints can be anything. Yeah. Okay, but black box is slower. Okay, so it's important that we try to do something smart here. So we'll do a relaxation of the discrete parameters, and for the z's, which are the choice of which steps even, that is a combinatorial. You have to do that with some combinatorial thing, like integer programming or something. Okay, so, but what ADMM does, it's just an abstract framework. You can plug in different options for each of these things. There's a wide literature on all of these types of subproblems. What we'll use as subproblems. Okay, so this general framework allows you to have, you know, an arbitrary number of actual optimizers. In these slides, I've listed different options you can use for each step. Some different options. Now, random search. Have you ever tried random search? It sounds really stupid, but it's actually very hard to use. But we beat it. Thank God. The 2 things that you can really get your hands on these days, more or less, are these 2 things that are open source. And we showed that we beat them pretty handily. That took time. So we have a decent-ish optimizer, at least, for this problem, even though this general problem is a mixed integer nonlinear program. You know, when you say that, and black box. So when you, with constraints. So when you say that to an optimization person, okay, we're only going to be able to do small problems. Indeed, we're not talking about lengths of, a pipeline of length or DAG of 20 steps is still 2 time consuming for this. But, you know, that's probably about the limit of, we can get there. That's probably about what real data science pipelines look like. They're not really 500 steps or anything. Okay, let me just go a little quicker now. Let me just say that in this framework, it turns out there's an elegant way to add constraints so that it doesn't change much the problem, the solution. Okay, I'll just leave it at that. We can handle these black box constraints. Okay, this is just showing that, indeed, when you have constraints, formulating the problem with constraints, because you can just search without the constraints. But when you try to enforce constraints, it does help. That's all this is saying. And when you have restrictive constraints, you really have to do the enforcement of the constraints. Okay, so that's it for this part. It's just saying that particular challenge, we can sort of have something decent. The next version we're working on now is, that's for a fixed length pipeline. Because any optimizer typically, or any standard optimizer, like a mathematical program type optimizer, typically deals with a fixed number of variables, as that does. This is how you might do a variable length solutions. Try pipelines of all different shapes and lengths. Okay, using ADMM, this ADMM thing as a building block. Okay, so how might we, so that's fine, maybe it resolves some issues. But then there's the practical tool. So even if we call this Auto AI, some kind of new tool that data scientists can use, this is interesting to go into in depth. I'll just mention one thing. There's a trust issue that we find when we interview data scientists. Even when they see that it gives them better results than their own results, they still trust their own bet more. Okay, so what that tells you is, one thing it maybe tells us is that they need control over the thing. They don't want to just hit go, and something happens, and then they look at the pipeline. They want to control it more. Then they'll trust it more. Okay, we'll come back to this if you want. This is a little, it started out as a programming language. To somebody's question. It started, when I was talking about a grammar, you'd think, well, this could be a programming language. Yes, and that's where it would enforce those types the way you do in types that define the inputs and outputs of each node. But we have another kind of type here, which is a little novel, I think, which is about how you control it, how you say which things you want to optimize for. This is just saying, if I want, I'll just show you some examples. If I want, here's what it looks like in code. You can use it within scikit-learn. You can use it within Python. So it's not some funny. And we changed it so it's actually a library to make people more comfortable. The type stuff is under the hood. It just makes sure that you can't make errors. Back to one of the original questions. This machinery makes it, in a Python interface, you can do things that are like the things you normally do, but certain errors can never happen. Okay. Furthermore, through a type system, you can specify examples like this one at the top, where I say, look, I know that this first part of the pipeline, or DAG, I want to do this way, these exact steps. However, if you want, you can search the hyperparameters for me. I don't have time to do that. That's when it's in blue, light blue. If it's dark blue, you're saying, you know what, search even the discrete choice for that step within, try these 9 different things and their hyperparameters. Okay, so that gives you some control. You say which parts you care. Look, whatever you do, I want an SVM. Okay, but if you want, do all the data prep steps however you want, or whatever. This is just showing you a little bit what it looks like in code. This is an alternate way, the Unix type way to specify pipelines. It should be fairly natural. You see these double arrows and so on, ands and ors. Okay, so you can play with this if you want. This is just showing you that you can make your own little library of prepackaged search spaces. You can think of these things as search spaces. You can have your own medium, large, and extra large, where you're trying all different things. You can very easily, in this little language, specify something with over 1 million combinations. Now that could be bad, that could be good. But at least specifying what you want to do is very compact. And then that's the programmatic interface, but then for some users they may want a graphical interface. That's an ongoing research thread we're working on too. This is one thing that's pseudo upshot, which is if pipelines are the main object, then comparing pipelines and other things you want to do with pipelines you should focus on, as opposed to the usual things that are only about models. Well, let's look at the ROC curve of the model. Let's look at whatever. This is saying pipelines, maybe you should put special effort into comparing pipelines, for example. Okay, so I'm almost done. So here were the 2 key ideas, really. Sort of one idea. The model is the pipeline, or the pipeline is the model. Okay, and in the end, and we make all of data science one optimization. The big idea. You can see that there are many, many more things that we could do, one can do in all of these categories, including some, say, statistical theory around this new machine learning method, and so on, and making the real system, and ACI issues, programming language issues, and so on. These last three I'll just mention. There's even bigger open questions. One of them I'm actively working on, which is how to actually put in domain knowledge, like the knowledge of how loans work or how medicine works. Streaming is a big one. Nick and I have been talking about that. Nick is an expert on this kind of stuff. But data science tools today are not streaming, but the real world in general is streaming. Because every data set that you get is just a snapshot of an evolving distribution. And you're in an enterprise setting, especially, new data comes in every day. New training data and new test data. So the true statement of the problem is a streaming statement. Okay, but I don't know how to do that yet. So maybe talk to Nick if you're interested in that. We may start working on that. Unsupervised, this is all just supervised learning right now. You know, well-established theory, well-defined problems. Could you do this for unsupervised learning, where the output is qualitative insights? Could you do any kind of automation? I claim yes. So, but that's later. How much? We don't know. Obviously, there has to be a human in the loop, much more tightly. And then I only dealt with these first three issues, or at least tried to deal with them. There are many, many more issues I feel are open in data science. And I'll just leave this up here if anyone wants to stare at this. And otherwise, thanks for your attention. I hope it was non-sleep inducing.
We have time for just a couple of questions. Please wait for a mic, maybe back there.
Yeah, so thanks for the talk. So my impression of most sort of data projects is that when people are trying to sort of figure out what the actual goal is, the answer, like when the data scientist asks, like, okay, what do you, like, sort of other business unions, for example, like, what do you want to do? My sense is often the answer they get back is like, well, what can you do? So I'm wondering, I mean, in particular, sort of if you saw any particular results in the CSCW paper you mentioned about how this tool is used for sort of, or potentially open area or open questions in sort of exploratory data analysis, or sort of the actual sort of social process of setting goals for big data projects.
You're asking about how can we, at the beginning of a data science project, how can we say the kinds of things that are possible?
Yeah, more or less. And how does that interact with sort of users?
Well, so at least with what this is doing, this is taking a kind of problem as, this only works if you're doing supervised learning. So whatever your problem is, but that's 99% of what everyone means by data science. So it's not that restrictive, but still, you got to mush your problem into that framework. So that's one quick answer. It has to, at least for this, and most real data science, that's what is meant. But I would say what's possible is more, only researchers know that. So researchers know all the things that are possible. And so I often do have a situation where a CEO or chief data officer or whatever of a big company, what can we do with our data? We have this interesting data. What can be done? Most things that people really end up wanting to do, more or less, are supervised learning. can be mapped to that. But, you know, there are things beyond that, and the only way to answer that is a researcher has to talk to them. because the research literature is the space of all things we can do. But, so I don't know if that, but talk to me after if I didn't address your question.
Hey, so end-to-end differential programming seems like a great fit for this problem. So maybe you're familiar, maybe you're not familiar with the efforts in Swift for TF, so Swift for TensorFlow, they're implementing differentiability into the LLVM compiler and all these things. So certainly some of these things don't have gradients, right? Like picking K for K-fold validation, it'd be tough to imagine a way that you could define gradients as a function of K. But a lot of them have subgradients, and you could kind of imagine some sort of gradient definition for differentiating with respect to K. Have you guys considered this?
We are considering it, yes, and it's a great connection. Yes, that would be taking a very neural netty view, which should absolutely be done. He is starting that, so if that's something you're interested in, talk to me.
Okay, that's all the time we have, so let's thank Alex. Thank you.